Section 13.4, motion along a curve. And this is practice problem number 7. Once again, given an acceleration curve and boundary conditions, we're going to try and reconstruct the velocity and the position. First, the velocity. We know that v is equal to the integral of at dt, and vx is going to be equal to the integral of -3 cosine of t dt. That's going to be equal to -3 sine of t plus c1. v naught is equal to 0, and of course at 0, sine 0. So this is already 0, c1 is equal to 0. vy is equal to the integral of -2 sine t dt. The integral of -2 sine t is 2 cosine t plus c2. The boundary condition is 2. At 0, cosine t will already be 1, which makes this 2, so t2 is 0, or c2 is 0. Okay, vz. The integral of 0 dt is equal to 0 plus c3. Finally, we have a boundary condition that produces a constant. Because vz should be 1 at 0, c3 has to be equal to 1. That produces our velocity vector. Vt then is equal to -3 sine t, 2 cosine t, and 1. Okay, r of t, we know then is equal to the integral of v dt. Rx is going to be equal to the integral of -3 sine t dt, and that's equal to 3 cosine t plus c4. R naught is 3, and this already produces 3, so c4 is 0. Ry is equal to the integral of 2 cosine t dt, and that's equal to 2 sine t plus c5. Ry is supposed to be 0 at 0, and this already produces 0, so c5 is 0. Rz is the integral of 1 dt. That's equal to t plus c6. R naught is supposed to produce 0, which it already does, so c6 is 0. So that makes our r function equal to 3 cosine t plus 2 sine t, comma 2 sine t, and t. So given the acceleration and boundary conditions for r and v, we can actually reconstruct r and v.